Okay, so let's talk about interference. This is one of the most interesting properties of waves, and it's something that's kind of unique to waves. And there are lots of different applications of this, lots of different ways that you can observe it, but for now we'll just do sort of an intro, and then we'll talk about a few of the ways that we can observe it. Okay, so here I have two pulse waves moving towards each other. And we notice that both of these have a pulse in the same direction. They're both going upwards. So as these waves move closer to each other, they will start to overlap. Oops, there shouldn't be an arrow here. So we can see here they've moved together, they're starting to overlap. When they actually overlap completely, their heights will add together. So this combined pulse is supposed to be as tall as this height plus this height. So however tall this is plus however tall this is, when they combine together, those heights add, and for just a second, it's taller than either of the individual pulses that went into it. And then after it's gone by, each of the original pulses still has its same shape, its same height, and is still moving in the same direction as before. So they basically move through each other, add together for a brief instant in time, and then move past each other as if nothing happened, each with their same original height. And we call this constructive interference. Because we're kind of constructing a bigger wave than we had to start with. So I take both ends of the slinky and raise them up, and then we see that in the middle there, we get a higher peak than either of the two parts that went into it. After the two waves pass each other, you can see them kind of split apart into the two humps again, but because of the friction on the paper and because of other things that we'll talk about pretty soon, it's not quite as clean as you would expect. You would be able to see this effect better on a much longer slinky. All right. Now we have a similar situation, except that one of these waves is going up and one of them is going down. So as they move towards each other, again, they're going to start to overlap. Look something like this. And then when they completely overlap exactly, they could, if they're the same height up and down, they could completely cancel each other out. In the same way that +5 and -5, when we combine them together, we get 0. If this has a height of +5 and this is -5, they combine to make 0 as they exactly overlap. And then once again, they would move past each other, each having its same height as before. Cool. So we call this destructive interference. So as I move, I'm making two different direction pulses from the two ends of the slinky. On the left side, it's going down. On the right side, it's going up. And then as those two pulses meet each other, they flatten out. This was super quick, so I had to really slow it down a lot. And then if we had two waves in the same direction again, they're both down this time, but it doesn't really matter. Again, they would combine to make a bigger pulse, and then they would move past each other, return to their original shape, and keep going. So as waves overlap each other, their shapes can affect each other, add together, or subtract. But then once they are moved past each other, each one still has its original shape. So as I move the two sides down, I get a stronger pulse in the middle as they overlap in the down direction. This would still be considered constructive interference because it's not about whether it's up or down, it's about whether the result is a bigger difference from the middle or a smaller difference from its resting position. And as you can see, this creates a bigger difference from the resting position when the two downward pulses overlap each other. Okay, so this is looking in one dimension. The same thing could happen for a longitudinal wave. And in that case, the up and down drawings would indicate like a compression or a rarefaction instead. All right, now let's look at this thing. Looks a little bit crazy. What it is great. All right, what it is this is illustrating what happens when we have two sources of waves next to each other. So you could picture this as looking at the ripples in a pond when you drop something into the pond and cause a wave there. And we have two sources of ripples next to each other, and we're kind of looking down from above. So these, I drew them with different thicknesses to help you see more easily which sets of waves go together. But these thicker lines are representing the ripples coming from this source. So the red represents a trough, and the green represents a peak. So it's moving down, up, down, up, down, up, down, up. So this is this wave spreading out in ripples from this location. And then the thinner lines are the same thing from this location. So we have a peak, a trough, or sorry, the red is a trough, a peak, a trough, a peak. So the thinner red and green lines represent the ripples moving out from this source. You can get these ripples a few different ways. You could have two things dropped into a pond simultaneously. But another way that this often happens is if you have waves coming towards some kind of barrier, and then you have two separate holes in that barrier that it kind of acts like two different sources of the wave. Sometimes these are called slits. So this is also called a double slit pattern. But you could call it a double source pattern because really it happens anytime you have two sources. But if you're doing something with, for example, light waves, then one way to get sort of two sources is to take a barrier that light can't get through and then cut two slits in it so that the light can get through in just those two places. Okay, so let's look and see what we see going on here. Right down the middle, we see a peak and a peak, trough and a trough, peak and a peak, a trough and a trough. So along this line, we can see that the red and green are always lining up with each other, which is going to cause the two waves from the two sources in all of these places to interfere constructively, to add together, because the high points are overlapping with the high points, and the low points are overlapping with the low points. So here we're going to get constructive interference. But in other places in this pattern, we kind of see the opposite thing. Right here, we see a red line and a green line overlapping, meaning we have the top of one wave and the bottom of another wave overlapping. And when we get that, they end up canceling out. So I'm going to draw little X's here where the red and green are overlapping with each other, and that's going to cause destructive interference. And then we have the same thing going on down here, red and green overlapping. The top of one wave lines up with the bottom of the other wave. That's going to cause destructive interference. So as we look at this type of pattern, and if I were to continue these lines out, we would see another constructive spot and then another destructive spot. We get this alternating pattern at different angles of constructive interference and destructive interference. But it's still the same idea. When the top lines up with the top or the bottom lines up with the bottom, we get something like this, where the wave gets stronger. If a top lines up with the bottom, we get them canceling out. So this would still be considered constructive. All right, I decided to take example number 5 and give it a little bit more room and color code it to make it a little bit clearer. So here I have two waves moving towards each other. And they don't represent like up and down anymore, the colors. They're just representing the two waves so that it's a little easier to see what happens as these waves start to overlap. So I'm going to draw the red wave and the green wave separately for each step, and then I'm going to show in blue what we would actually see as a result, what the combination of those things is. So as these waves start to overlap, this part of the red wave and this part of the green wave will end up in the same place as they move towards each other. So I'll take the red wave, I'll draw it like that, and then the green wave has now moved towards it, so the green wave is now like this. So now, in the places where there's only one wave, the result is going to just be whatever that wave is. And then in this place where they overlap, we have both the red and the green. That's going to add together. So we're going to have a deeper trough in this one spot where they're overlapping. And then it's going to continue on where we only have just the one wave. So as they overlap with each other, the first thing that we see is kind of this one deeper trough with the rest of it being kind of connected. Now let's see what happens as they continue moving towards each other. So I'm going to draw this same shape for the red wave. And then the green wave, now this was lined up with this, now it's going to be lined up over here. So it's even further into overlapping. So we still have these same two shapes, but now they're overlapping more. Now let's see what's going to happen with the combination. So where I only have one wave, that's the only wave that I see. And then here, we've got a top and a bottom lined up. That's going to completely cancel out. We have another top and a bottom lined up. That's going to cancel out. And then we're going to continue to have just the one wave. So at first, we got this deep trough, and then as they started to overlap more, they canceled out. Okay, let's have them keep moving. So I'm going to draw this same shape again for the red wave. And then the green wave, this first trough of the green wave was lined up here. I'm going to move it over a little bit more and put it here. Okay. So now I have this combination, I have this combination, I have this combination, and then it's continuing from there. So now I have more of the wave where they are overlapping, causing a result to be really big. Now as they continue moving through, I'm going to have them line up exactly. So here's my red wave. The green wave has now moved completely on top of it. And we can see that all the tops of the red line up with the bottoms of the green and vice versa. So everything gets canceled out. And then as they keep moving, now the green is going to be partly moved past the red wave. So we have it like this. Again, we're going to have these extra tall parts of the wave where the peaks and troughs line up with each other. And then it would kind of continue like that as they finish moving past each other. So when we have waves moving in opposite directions that have a repeating cycle, like these red and green waves, we get alternating between constructive and destructive interference. And I drew the red and the green waves with just 2 cycles each. But really, when you have 2 periodic waves overlapping each other, this pattern would keep repeating. So we have constructive, destructive, constructive, destructive, constructive, as these 2 waves with the same wavelength moving in opposite directions overlap each other and interfere. An easy way to get this to happen is to set up a certain width where the waves get reflected back and forth along that width. So you can see that happening with the slinky. So as you can see, when I make a pulse on one end of the slinky, starting from the right here, it reaches the other end and it reflects, meaning it gets to that end and then goes back the other direction. And when it reflects, you'll notice that it also changes its direction. What started as a pulse going up turns into a pulse going downwards. So this is important to the effect of the standing waves. We've been looking at transverse waves so far, but you can also have a wave traveling in a longitudinal wave in a slinky, and you can see that this also reflects off the other end. You could also get standing waves that are longitudinal waves, but they're just a lot harder to see easily in this type of setting. And when this happens, we call it a standing wave. A standing wave is basically just made out of waves moving in opposite directions, causing a repeating pattern of constructive and destructive interference. And what ends up happening is that instead of the waves looking like they are moving from right to left, we just see the shape get taller and smaller while kind of staying in the same place, because the two movements are kind of canceling out and the waves are either overlapping constructively or destructively, alternating between the two. For a standing wave to work, the wave has to line up perfectly with the width. So one way you can have this happen is with the entire width taking up only half of a cycle. It's either only got the up or only got the down at a time. Here you can see a standing wave made on the Slinky. I'm not moving my fingers very much, but I'm still getting a huge wave on the Slinky, and that's because when the wave bounces off that other end, it creates another wave moving in the opposite direction, which on a standing wave means it alternates between interfering constructively and destructively. So when the middle of the Slinky is all the way at the top or bottom, that's that constructive interference. And then when it stops in the middle here, or when it's in the middle, it doesn't actually stop because it's moving through the middle, that is the destructive interference. Or you can have the width take up one entire wavelength, meaning if I were to trace one of these lines, it would include both a peak and a trough. And then we see these two kind of places where the wave is moving up and down. And then at the two ends and in the middle, it's not moving. We call these places an antinode. And then a place where the wave is not moving is called a node. Here's another example of a standing wave on the Slinky. Now we can see we have these two regions of the Slinky that are moving up and down really quickly, but actually in the middle, it's pretty much staying lined up right there. So this wave has half the wavelength and twice the frequency of the previous one, but it still fits evenly into that length of the Slinky, meaning I'm not having to move my fingers that much to get this really big wave, because at certain times it's interfering constructively to make a bigger wave. You can keep getting more standing waves by moving faster and faster. Raising the frequency lowers the wavelength and makes more waves fit in the width. But those waves need to fit exactly or it won't really work. Like, you can't have it be not lined up. It won't create that nice repeating consistent pattern. Now let's see an example where I'm not wiggling the Slinky at the correct frequency. So what that means is that I'm not getting that standing wave. I'm not seeing a consistent pattern of which part of the Slinky is moving up and down and which part is not. The whole Slinky is kind of moving, and it's not moving nearly as strongly in the standing waves, even though I'm moving my hand probably even more. And that's because it's not the correct frequency. So the wavelength does not fit along the length of the Slinky in the correct way to make a standing wave. The waves do not line up with each other correctly. Here's an even faster standing wave that has 3 regions that are moving up and down. It's not quite as even, and that's because it's pretty hard to move my hand fast enough to make this standing wave. The frequency is higher than the other two. And this is slowed down a fair amount. But you can still see this alternating pattern between having sort of an N or W shape versus being briefly interfering destructively and being basically flat. When you do have a standing wave, when you get the frequency just right to allow the right size wavelength to fit in that width, that is called resonance. So if you shake the slinky at the wrong frequency, you won't get this nice overlapping pattern because the wave will not line up correctly. But if you shake it with the correct frequency, then that frequency will determine a wavelength, and if that wavelength fits into the length of the slinky correctly, then it won't take very much movement to get a really big wave going on the slinky. And we call that concept resonance. When you shake something with just the right frequency, you can get a really strong wave response, and that has to do with the wavelength associated with that frequency compared to the geometry of the object. Hope this was helpful. I hope it was interesting. We'll keep seeing interference as it applies to different types of waves like light waves and sound waves.